the recording? Yes.
Okay, thank you, sir. So, very good afternoon to everyone.
Nisha, your video is in switch off mode. Yeah. Now it's fine.
Um, so,
Okay, go ahead.
very good afternoon to everyone. My name is Nisha Singh. I'm pursuing master's degree at IIT Hyderabad. I feel honored to extend my warm welcome to all present here. On behalf of IS Structured IIT Hyderabad student chapter at Earthquake Engineering Research Center, I want to take this opportunity to welcome our honorable guest, all the faculties, industry people, participants from the academia, research fraternity, and all the students to join the webinar on the topic Earthquake Performance Assessment of Buildings Non-Linear Static Analysis. So today we have the privilege to have with us an expert in the field of structural earthquake engineering who shall be reflecting on the theme of the webinar. I would like to introduce our keynote speaker of the day, Dr. Mitesh Surana, to our esteemed audience. So Dr. Surana is currently working as an assistant professor in the Department of Civil Engineering at IIT Ropar, Punjab. His expertise includes performance-based seismic design, seismic fragility analysis of structures, seismic design of non-structural components, earthquake loss estimation, and traditional and contemporary housing stocks in the Indian Himalayas. Dr. Surana has authored 40 peer-reviewed articles in national and international journals, conferences, and for his academic excellence, he has been awarded the Indian Services of Engineers Award by IIT Roorkee. Dr. Surana is involved in several research projects funded by the Government of India and other agencies, including the National Disaster Management Authority, International Division of Department of Science and Technology, Science and Engineering Research Board, Ministry of Environment, Forest and Climate Change, and Satluj Jal Vidyut Nigam Limited. Dr. Surana is also a recipient of the Jai Krishna Award and the Hanumantacharya Joshi Award by the Indian Society of Earthquake Technology. So this is a brief introduction of our keynote speaker, Dr. Mitesh Surana. So now before we start the event, a small announcement for all the participants. If you have any queries, questions, doubts or clarifications, please do type your queries in the chat box only. We'll have sufficient time for the discussion in the end, where Dr. Praveen Kumar Venkat Rao, faculty advisor of the student chapter, will be the moderator. So now without any further delay, we'll turn the time over to Dr. Surana. Sir, over to you.
Okay, thank you, Nisha, for introducing me. I hope I am audible, and let me share my screen as well.
Yes, sir, you're audible and
Can you
your screen is
see the
shared.
screen?
Yes, sir.
Okay,
Yes,
fine,
your
fine,
screen is
fine.
shared.
Thank you, Praveen, for confirming. So, let us begin our discussion on the topic earthquake performance assessment of buildings, and here we will focus primarily on nonlinear static analysis. So, just to begin with this topic, I have subdivided this presentation into 5 different subheadings. So first we will discuss about structural and seismic analysis, then how we design structures using the conventional approach that is being used in our building codes, for example IS 1893, that is called force based design. Then after we will understand that what is actually aim of seismic design and what are the limitations that are associated with force based seismic design, that we will try to understand. And then we will move to performance based seismic design, where we will discuss mainly about nonlinear static analysis and the other associated features of performance based design. And finally we will be summarizing what we have discussed in this lecture through concluding remarks. So now coming to the first part of this presentation. So first we need to understand what we mean by structural analysis and seismic analysis. So let us try to understand first the structural analysis. So as we know that as a civil or structural engineers, we are always interested in determining forces, displacements or reactions in any structure. So this art of predicting likely performance of a structure under a prescribed loading we define as structural analysis. Performance metrics of interest for our for civil or structural engineers are particularly forces or stresses. It can be only one type of force, for example bending moment, shear force or axial force. It can be all type of forces. Similarly, stresses can also be a single type or uniaxial stress. It can be a resultant of multiple stresses acting on a body or a system. And then displacements or rotations are the other response quantities of interest. And sometimes we are also interested in knowing the support reactions. So all these quantities we determine when we perform structural analysis. The simplest example to understand it could be a beam or a column, or analysis of a simple truss and other frames and other structures. So in all type of these analysis, we determine forces, displacements, and support reaction. Now these analysis inherently involve some assumptions. What are those assumptions? Whether the structure or the system which I am analyzing is actually behaving in a linear manner, non-linear manner, elastically or inelastically. So depending on the type of the loads which we are considering and type of structures we are considering, there can be assumption of linear elastic behavior, then the non-linear behavior of the structure as well. So depending on what type of load we are focusing on. So conventionally, we study linear elastic analysis of structures at the undergraduate level, because all the methods that we learn during our undergraduate studies in civil engineering curriculum, those are particularly based on assumption of linear elastic analysis. What we mean by linear analysis? Linear analysis means the material or the system which we are understanding actually follows the Hooke's law. That means stresses are proportional to strain, or stresses are within the elastic limit. Similarly, what we mean by elastic analysis? Elastic analysis is that the material or the system which we are analyzing, actually in that particular system, the loading and unloading follows the same path. If this assumption is violated, then that type of system is classified as inelastic system. So primary assumption when we study any type of structure or a beam, frame, or any other structure, the primary assumption we take is of linear elastic behavior of the structure. However, we will see that in case of earthquakes, the assumption of linear elastic behavior is not true, and we need to understand about non-linear analysis. So this is why we need to understand that non-linear static analysis particularly, because this forms the background to understand how the actually structure behaves during earthquake and how we can determine their actual response. So therefore it becomes essential to know first the linear elastic analysis, and then we can proceed to non-linear analysis. So I am assuming that all the participants have enough background on linear elastic analysis, and I will mostly focus in this presentation on non-linear analysis. Now coming to seismic analysis. So as you may be familiar that there are a variety of seismic analysis that are recommended in building codes. For example, the first and the simplest method that we use in our analysis for earthquake forces is called equivalent static method, which is based on the assumption that the response of structure is governed by a single mode of vibration. So when we talk about the response of a structure governed by single mode of vibration, that means the structure is low rise. So fundamental mode is well enough to capture the response of the structure. That is the inherent assumption that is being involved in equivalent static analysis. And accordingly, the code defines that this type of method is only applicable when certain conditions are satisfied. What are those conditions? So the first condition is that the fundamental period of the structure is less than 0.4 second. Second condition is that height is less than 15 meter of the building that we are analyzing. Then it is in low seismic zone and it is of regular configuration. So under all these assumptions only we can perform the equivalent static analysis. If these assumptions are violated or any of these assumptions are violated, then in that case equivalent static analysis cannot be performed. Then we need to move to another type of analysis that is called linear dynamic analysis, and linear dynamic analysis can be performed in two ways. The linear dynamic analysis can be performed either using a response spectrum, and linear dynamic analysis can also be performed by using an actual time history, that is the earthquake record that we can use to perform the linear dynamic analysis. So what is the difference between equivalent static and linear dynamic analysis? In equivalent static analysis, we are assuming that the structural response is governed by the single mode of vibration, whereas in the linear dynamic or response spectrum analysis, we are using modal superposition method. That means we assume that the structural response is a combination of structural response is governed by a combination of different modes and by different types of combination techniques. For example, square root of sum of squares, or complete quadrature combination, we combine the structural response of interest. It can be stress, force, or displacement to obtain the structural response. In what cases we can apply this linear dynamic response spectrum analysis? For all the cases, linear dynamic response spectrum analysis can be applied, and uh, except where equivalent static method we are applying, in those cases also the linear dynamic or response spectrum method can be applied. But the cases where equivalent static method is not applicable, then we need to go for linear dynamic or response spectrum analysis. The second variety of linear dynamic analysis is linear dynamic time history analysis, where we choose actually the recorded earthquake ground motion to obtain the response of structure in terms of forces, displacement, or any stress resultant of interest. So here, when we perform the linear dynamic analysis using a time history, then we need to select appropriate earthquake records, then only we can perform the analysis. And it is not only to select those earthquake records, because different earthquakes have wide variation in terms of their magnitude, source to site distance, then their amplitude in terms of acceleration, their duration, then their frequency content. So those have to be matched with respect to our site specific requirement. That means where the building is located, what type of amplitude of earthquake, duration, those things we can expect at that particular site. Accordingly, I may need to modify the frequency content of a given recorded earthquake, or I need to scale them either up or down. So when we perform the linear dynamic analysis through time histories, then the selection of time histories, appropriate time histories, becomes a crucial issue. Now, moving to further complexity, if we want to understand how the nonlinear behavior of the buildings, how the building behaves during earthquake, so then we need to move to the nonlinear analysis. And the first category of nonlinear analysis is nonlinear static analysis, where we apply a monotonically increasing load over the structure and measure its structural response. Before that, it is to be kept in mind that it is not directly that we are applying the load. Before that, we also need to develop a detailed nonlinear model of the structure. That nonlinear model should incorporate the effect of material nonlinearity as well as the geometric nonlinearity that can be expected in a particular type of structure. So to understand or to perform this nonlinear static analysis, first we need to understand nonlinear behavior of the structure, how a structure behaves during earthquake particularly. And then we need to also choose an appropriate loading pattern, because we are applying to a structure a monotonically increasing load. So what should be the pattern of the load? Because my structure is of multi-story, so how the load will be varying around the height, whether it will be linear, parabolic, constant, or some other variation. So that also I need to know, then only I will be able to predict the response of the structure accurately. So there are different varieties of the loading pattern that are being recommended in literature, that can include the loading proportional to fundamental mode, that is called single mode based pushover analysis. Then there can be loading based on combination of multiple mode, and that is called multi-mode pushover analysis. Then there can be adaptive type of loading. Adaptive loading means the loading which changes with each instant of time while we are applying the monotonically increasing load. So because of the change in the dynamic characteristics, particularly due to change in stiffness after yielding of the members, the change in the structural mode shape occurs. So to take into account the change in the dynamic characteristics of the structures, we need to adopt for adaptive type of pushover analysis. So these are different varieties of pushover analysis that can be conducted. So pushover analysis and nonlinear static analysis are synonym to each other, so they can be used interchangeably. Now, coming to after choosing this lateral load pattern, there are several other issues that comes into picture when we perform nonlinear static or pushover analysis. And the next important issue that comes is the selection of backbone curves, how the force displacement behavior of member will look like. So we need to understand how actually the backbone curves for different members of our structure will be. For example, how the backbone curve will be for a beam, how the backbone curve will be for a column, how the backbone curve will be for an infill wall, and so on. So this also we need to understand. Then if we come to the last category of analysis, that is called nonlinear dynamic time history analysis. So nonlinear dynamic time history analysis, we need to this is the most complex analysis that we can conduct to assess the earthquake performance of any structure. And again, in nonlinear dynamic analysis also, there are several variations that we can encounter. And those variations are called cloud analysis, incremental dynamic analysis, multiple stripe analysis. So these are different types of nonlinear dynamic analysis. So conducting, whether we are conducting cloud analysis, incremental dynamic analysis, multiple stripe analysis, the analysis procedure remains same. It is only the selection of the ground motion that we are using to conduct nonlinear dynamic time history analysis that differs in these different types of analysis. Then apart from this, when we are performing nonlinear dynamic time history analysis, we are analyzing structure actually during structure subjected to earthquake loads. Therefore, we need to incorporate the member force displacement relationship appropriately by choosing the appropriate hysteresis model that takes into account the effect of cyclic loading, reverse cyclic loading that occurs during earthquake, and how the material or the member will degrade with continuously increasing the displacement cycles over the time. So that effect also we need to incorporate in our analysis model. Over and above that, selection and matching or scaling of ground motion will be applicable in this case also, because we are performing a time history analysis which is similar to a linear dynamic time history analysis. So in linear analysis, the model which we are using for our structural design, that is fine enough. Only we need to conduct time history analysis by choosing the appropriate ground motions. But when we are performing non-linear dynamic time history analysis, then we need to develop a non-linear structural model first by incorporating appropriate hysteresis model and member force displacement relationships. Then only we can compute the structural response. So if we see the complexity and simplicity of these type of analysis which we have discussed for estimation of seismic response of structures, so equivalent static method is easiest and it requires less computational effort, and nonlinear dynamic time history analysis is the most complex and requires more computational effort. Similarly, as we know that when we are performing the nonlinear dynamic time history analysis, the estimating is expected to be close to the actual response, or it is the most accurate method of analyzing structural response for a structure subjected to earthquakes. Now coming to the next part of the presentation, that is force based seismic design. That is what we do when we perform analysis using the current codes, for example IS 1893 2016. So in current code, we determine first the we can apply either equivalent static method, or we can apply linear dynamic method using response spectrum. So in both the cases, anyway we need to determine the horizontal seismic coefficient, that is representing a fraction of the weight of the building that is acting in the lateral direction for that particular building which we are analyzing. And that depends on the zone factor, where the building is located in which seismic zone. Spectral amplification that we can obtain through response spectrum and quantify in code as SA by G. Importance of the structure I, and the response reduction factor R. Once we know this AH as Z by 2 SA by G I by R, we multiply this quantity AH by weight, so that we can determine the design base shear VB equal to AH into W. So in this case, we can clearly understand that the forces that we are computing using current code method is actually based on prescription. Code writes the prescription that you do this, don't do this. So it is very simple to use. And if you see the forward of the code, it is intended that the structure designed following this approach will not collapse in case of major earthquake. But we are nowhere ensuring whether the structure will collapse or not. We are just relying on the forward that is written in the code. And the governing criteria that is being used in seismic design is force alone. So we are designing for force and later checking for the displacement. But the final design criteria is force only in the current procedure. If we see how these factors Z, SA by G, I by R, these varies. So for example, importance factor code defines three different categories. For lifeline and emergency building, code recommends 1.5 important factor. For community buildings, it recommends that 1.2, where occupancy is greater than 200, and all for all other buildings, important factor is taken as 1. So what we intend by this importance factor, that when we are designing a building using code, we should ensure that the lifeline building should not be go damaged to the same extent as we are expecting in case of a residential building, for example. And that is how implicitly incorporated in the code, by using increased importance factor for a lifeline or emergency building as compared to the residential building. Similarly, if we see the response reduction factor that are given in the code, so primarily the response reduction factor indirectly gives us an idea that how much ductility is available in that particular type of structural system. So if it is unreinforced masonry, it has less ductility as compared to reinforced masonry. Then if we have an ordinary moment resisting frame, then it has lesser ductility as compared to a special moment resisting frame, which is designed and detailed following the provisions of IS 1893 and IS 13920. So if we see a typical flow chart, that how we design a structure using the conventional approach that is given in IS 1893. So first we try to proportion the different members of the structure to and estimate their sizes, width and depth particularly. From that, after knowing the width and depth, we can compute the member stiffness. After knowing the member stiffness, we can compute the global stiffness or the structural stiffness and estimate the natural time period of the structure. Once time period is known, then we can compute how much will be the forces that structure will be experiencing in terms of base elastic forces using acceleration spectrum, and then we reduce it by response reduction factor to obtain the actual design force. Once we know actual design force, we analyze the structure and design for this, and then later check for displacement. If displacements are satisfied, then our design is okay. If displacements are limits are not satisfied as given in the code, then we need to revise the stiffness of the members. That means we need to reproportion the dimensions of the member that we have used for our structural design. Now let us try to understand that how actually we are designing these structures, from where the role of response reduction factor is coming into picture, from where the role of importance factor is coming into picture. So to understand this, first we need to understand the behavior of the structures under earthquake. So how the buildings behave during earthquake. So let's understand this by taking two different buildings. So the first building is a hypothetical elastic structure, which is we will not find in reality, but we are assuming this type of a structure as hypothetical elastic structure for our understanding purpose only. And the second is the real structure which we construct actually. So if I apply the lateral load on this hypothetical elastic structure and monitor the base shear that is going this building is going to experience at the base, and the displacement that is going to occur at the roof of this particular building. So if I monitor these two quantities, this displacement D and the base shear that is acting at the base of this building, and plot them on a graph between base shear to roof displacement, so I will obtain a straight line, because this structure is elastic structure. So it is hypothetical and elastic structure, so the force displacement relationship will be a straight line. Now if I see the force displacement relationship for the real structure, so in that is having identical stiffness as that of the hypothetical elastic structure. So the initial stiffness will match. After certain force, this structure will experience yielding, and its force displacement curve will become something like this. So this is the force displacement curve of a real structure, and the black straight line is showing the force displacement curve of a elastic structure. So it is easier to understand the behavior of elastic structure as compared to the behavior of the inelastic structure, which is the real structure. So to further understand the behavior of the real structure in more simplistic way, we also try to idealize the behavior of this real structure by representing its force versus displacement relationship in equivalent bilinear form. So we try to convert this force displacement relationship of this structure into two lines, which are representing the elastic or the linear part of the segment, and then this is the elastoplastic, or maybe depending on type of structure there can be strain hardening or strain softening in the structure. So real structure force displacement curve will be represented by two lines, and a hypothetical structure which is perfectly elastic, having infinite strength, will be represented by a straight line. So after understanding this behavior of a hypothetical structure and real structure, there are two important rules that we need to understand. The first is called equal displacement rule. So let us try to understand what this rule is. So if I have a hypothetical structure which is going to behave linear elastically during earthquake, then its force displacement curve can be represented by the black solid line as shown here. So it will be a linear, as we have discussed. And if I have a real structure, then its force displacement curve will be shown by this dashed red line as we discussed earlier. So the ratio between the ratio that sorry first we need to understand that this equal displacement rule suggests that the maximum displacement of an inelastic structure is actually equal to the maximum displacement of the elastic structure. So during an earthquake, whatever the maximum displacement that inelastic structure will experience, the same displacement is going to be experienced by the elastic structure. This is what we call equal displacement rule. So according to this principle, if we apply certain geometry, then we can estimate and determine that the response reduction factor that I can use for a structure is nothing but equal to amount of the ductility that is available in that particular structure. That means the response reduction factor is actually equal to the ductility ratio that is defined as the ultimate displacement to the yield displacement of a given structure. So ratio of these two parameters, the ultimate displacement to yield displacement, is actually representing the ductility capacity of the structure. So the maximum response reduction factor I can use for a structure is equal to the available ductility in the structure. And this principle is actually applicable for the long period buildings. That means the buildings that are having a period greater than 1 second are usually categorized under the category of long period building. In other words, the more advantage I can take in terms of response reduction factor if I have larger ductility available in my structure. So this is one of the important principle that we need to understand about earthquake resistant design. But keep in mind that code directly gives us the value of R. We are not estimating mu. Mu is indirectly incorporated in the code by ductile detailing. And therefore, for all the SMRF buildings which we are designing through code, will not result equal ductility, but we are using actually the equal response reduction factor for all those buildings. So this is where the problems arises in force based design, that for all the structures across the design space, we are using same response reduction factor, but they may not have the same amount of ductility available in them. This is the first important thing that we need to understand, that this is a particular problem related to force based seismic design. Now coming to the second type of principle that is also being used, and that is called equal energy rule. So this says that the energy stored in the force deformation loop of the inelastic structure is equal to the elastic structure. So energy dissipated in the force displacement loop can be represented by area of force displacement diagram or force deformation diagram. And if we apply certain geometry and equate the energy stored in the force displacement loop of elastic and inelastic system, we will be able to estimate that R is equal to square root 2 mu minus 1. And this expression is applicable for short period structures. That means the structures that are having period less than 0.5 second. So in long period structures, we have R equal to mu, and for short period structures, we have R is equal to square root 2 mu minus 1. That means, for example, if I have a long period structures, if I have a ductility ratio of 5, I can use response reduction factor of 5. Whereas if I have a short period structure, if I have a ductility ratio of 5, I cannot use response reduction factor of 5. The response reduction factor of short period building will be going to be less than 5. And for R equal to 5, if you compute for mu equal to 5, if you compute from this expression, R will come out to be 3. So we have only 60% of the ductility that is available. We have only 60% uh, the response reduction factor for the short period building is approximately 60% as that of the long period building. So this is another drawback that is not incorporated in our codes, and we directly take same response reduction factor irrespective of the period of the structure. Now coming to to understand about aim of seismic design, that what is actually aim of seismic design. So if we have seen the force displacement relationship for a structure. So for a typical structure, if let's say I develop the base shear versus roof displacement plot, we have seen that initially it will be elastic and there will be some non-linear part, and finally the structure will collapse at very large displacement. And accordingly, the different limit states on this curve can be marked. What are those limit states? Those limit states are whether the building after earthquake will be immediately occupiable, whether the life safety of the occupants will be ensured, whether the building will be prevented from the collapse or not. Depending on that, different amount of uh, member plastic rotation or displacements are permitted based on these limit states, and we can decide whether the structure can uh, be immediately occupiable after earthquake, or life safety of the occupants will be ensured, or whether the structure will collapse, depending on their permissible values and the actual values which are occurring in the building. We can determine whether the building will survive earthquake or it will collapse. So what we intend from this seismic design? From this seismic design, we intend that either the life safety of the humans which are there in the particular building should be ensured. Their life should not be in danger, or at least the structure should not collapse. This is the bare minimum which we are intending in our code currently, that structure should not collapse under the major earthquake. The other type of limit states that can be used, that includes that the damage in the structure should be limited so that it can be occupied after an earthquake. Or for example, if we are talking about some important structure, that can be a hospital or other lifetime building, lifeline building, for example a thermal power plant, nuclear power plant, then those should be operational even after the earthquakes. So therefore we are intending a different performance if we are designing a hospital or nuclear power plant or thermal power plant building. We are intending a different performance when we are target designing a hospital, a residential building, for example let's say life safety. So therefore their design should be different. Currently in the code it is accounted implicitly, not explicitly. How implicitly it is accounted? By choosing the importance factors. So we are using higher importance factor when we are designing operational performance. When we are designing life safety performance, the relatively the low importance factor is used. So it is actually incorporated implicitly, not explicitly, in our current force based seismic design. But our intent should be that we should ensure that the important structure will remain operational after earthquake, and similarly the residential building will be able to achieve the life safety performance objective, so that the lives of the occupant will be saved during earthquake, after an earthquake. So all these limit states that we define for a particular structure are actually representing the extent of damage that is experienced by a structure. Immediate occupancy is also representing some amount of damage in the structure, that can be in the form of minor cracking. Life safety is also showing some amount of damage in the structure, that can be in the form of very thick cracks. Similarly, collapse prevention is also showing us some amount of structural damage, that can be very extensive damage in the structure, falling hazards, and those kind of scenarios. So uh, depending on the limit state of interest, the extent of damage in the structure will be different. And finally, at very large displacement beyond the collapse prevention, there will be certain point where the structure will lose its capacity to carry even the gravity load, forget about earthquakes, and then it will collapse. So that limit state is marked here as the collapse limit state. Now each of these limit states are associated with some amount of economic loss. For example, let's say if you see these three scales, so first scale is showing the percentage of replacement cost that is required at different damage levels of a particular structure. The second scale is showing the amount of casualty that we can expect, that is represented by casualty rate. And the third scale is showing the downtime, that means after how much time that building will be again functional. So that is showing in the third scale. So if we see, let's say at immediate occupancy, because it is just the building will just start initiating cracking and all those things, so there we expect a less amount of replacement cost that we need to involve in the repair of these type of cracks, where for similarly we have less chances that there can be any casualty when the building is experiencing IO limit state, and it can be easily occupied after minor repairs, so there will be less downtime. See, in contrast, if we go near to collapse prevention or collapse limit state, the building will be at the verge of the collapse. That means we cannot repair that particular building. The building has to be demolished and then reconstructed. So accordingly, near the collapse prevention limit state, I need to invest 100% of the replacement cost. Then casualty rate, because building will be just at the verge of the collapse, so casualty rate is going to be significantly higher. So 0.25 means that the 25% of the occupants may get casualties under this particular limit state. Similarly, the downtime will be also very high. For example, in IO it was only few days. In case of uh, uh, complete collapse prevention limit state, there can be a downtime up to years or several months to years. So all these three quantities we are representing by three D's. First is representing dollar, second is representing deaths, and third is representing downtime. So dollar, death, and downtime, these are the three D's which are essential elements, and our objective of seismic design is to minimize them. So minimization of 3Ds is the prime objective of seismic design, so that we are able to achieve a perfect seismic design. Now let us try to understand the performance based seismic design, what performance based seismic design is, and how it actually overcomes the limitation of the force based seismic design that is being currently adopted in our code IS 1893. So in performance based seismic design, first we decide that what performance I expect from my building during earthquake. For example, I can expect life safety if I am designing a residential building. If I am designing a let's say a hospital building, then I can expect operational or immediate occupancy performance level. So first I need to decide the performance objective. Once I know the performance objective, I need to develop a preliminary design. That preliminary design may be based on the codal recommendation that we have for the force based design. After designing that structure, I need to assess its seismic performance. After assessing its seismic performance, if that performance meets my objective, which I have assumed initially in terms of whether I am targeting life safety or immediate occupancy or operational performance, if those performance objectives are meet, then in that case my design is done. If those performance objectives are not met after performing this preliminary design, then I need to revise the design to achieve the targeted objective, and accordingly I need to either increase the design force or reduce the design force to achieve a targeted performance. So this is how the performance based seismic design goes. Now let us try to understand different performance level that are defined in various building codes. So there are two building codes that I have listed here. One is FEMA and another is Eurocode. So what performance actually we want to expect from our building is actually depends on for what purpose that particular building is to be used. If building is used for some important purpose, then the performance should also be in terms of higher expectations. Similarly, if that particular building is to be used for residential purpose, then accordingly I can orient the performance objective. So there are different performance objective. They are in terms of definition, they are more or less same, but in terms of nomenclature, they are defined using different names in different codes. For example, operational performance level is defined in FEMA, but there is no definition of such performance level in Eurocode. Immediate occupancy is defined in FEMA, same in the Eurocode is defined as damage limitation. Life safety is defined in FEMA, same is defined as in Eurocode as significant damage. And collapse prevention is defined in the FEMA, and Eurocode it is defined as near collapse. So if I go from the top to bottom, That means I am increasing the amount of expected loss during earthquake in a structure. If a structure is performing operational performance level, it will be experiencing less loss as compared to if it is performing collapse prevention performance level. So higher performance results lesser loss, and lower performance results more loss. So let us try to understand now how we can assess the earthquake performance of a structure or a building that we are designing. So there are two procedures that we can follow. First is the nonlinear static procedure. Second is nonlinear dynamic procedure. So I will discuss in more detail about only nonlinear static procedure. Nonlinear dynamic procedure has not been included in this presentation. So this performance assessment procedure I can apply it for both type of buildings. That means a building which I am designing newly, or a building or that is actually, just a minute. Yeah, so this performance assessment procedure I can apply for two types of building. One is the existing building and the second is the new buildings. So key requirement is to apply this nonlinear static procedure for performance assessment of structure. I need to know the member cross section sizes as well as the reinforcement detailing in well advance. Then only I can develop a detailed nonlinear model of a structure. So therefore, to apply nonlinear static procedure, let's say if I am applying this procedure for a new building, then first I need to perform a response spectrum analysis or linear dynamic analysis using time history to obtain the section sizes and reinforcement details. If I know these details, then only I can develop the detailed nonlinear model of a structure that is prerequisite for conducting the nonlinear static analysis. Once I conduct the response spectrum analysis, after knowing the section sizes and reinforcement, I can develop the nonlinear model. After developing nonlinear model, I can perform the pushover analysis. After pushover analysis, I can estimate seismic demand and then perform the performance analysis. So this is the typical flow when I perform the nonlinear static procedure. In nonlinear dynamic procedure also, I need to conduct first response spectrum analysis to obtain the section sizes and reinforcement, then develop the nonlinear model, then develop the pushover, then perform the pushover analysis, then perform time history analysis, and then perform the performance analysis. It is essential and it is necessary to keep in mind that whenever we are performing nonlinear dynamic analysis, it is always advisable that we should always perform a nonlinear static analysis also, because the it is very easy to understand, it is relatively easy to understand the response that we obtain from a nonlinear static analysis as compared to response that we obtain from nonlinear dynamic analysis. So when we obtain the response from the nonlinear static analysis in advance before conducting the nonlinear dynamic analysis, then we get better insight into the behavior of the structure, that how it is going to behave during earthquake, and that actually helps us in understanding the response or the results that we derived from the nonlinear dynamic analysis. So it is always advisable to conduct first pushover analysis, then only go for the nonlinear time history analysis. Now, applicability of whether we are performing nonlinear static analysis or nonlinear dynamic analysis depends on the contribution of higher modes. If contribution of higher modes are not significant, then nonlinear static analysis could result you well enough results. If the contribution of higher modes are significant, in that case you need to go for nonlinear dynamic analysis as well. So if we are analyzing a complex or irregular structure or very important structure, in those cases it is preferable to always conduct nonlinear dynamic analysis also. Now let us try to understand that how we can develop the nonlinear model of a structure. So to understand or to develop the nonlinear model of the structure as a whole, first we need to understand the nonlinear behavior of the component or a member. And nonlinear behavior of a component means, what we mean by nonlinear behavior of a component, that can be a beam, a column, or a shear wall. So let us try to understand it with respect to a shear wall. So let's say I have a shear wall which is subjected to lateral loads. So this shear wall will be, when it is fixed at the base and it is subjected to lateral load. So as this lateral load is increasing, the moment at the base will be also increasing, because moment and lateral load in this particular shear wall, which is cantilever in nature, are related by the height of the shear wall, that is represented by LB. So after a certain threshold, when this
force will reach a certain threshold, there will be cracks that will be developed at the base of this shear wall. Why the cracks will develop at the base of the shear wall? Because the moment that this shear wall is experiencing because of this lateral load is maximum at the base. So near at the base, there will be some amount of cracks that will develop. With further increase in the loads, the cracks at the bottom will get widened, whereas there will be cracking which will propagate from bottom to top. So cracks will be propagated from bottom to top, and at different locations, cracks will also be developed in the tension zone, particularly at the towards top side also. Not at the topmost face, but it will propagate from the bottom to top. And there will be certain point after which the this shear wall will completely experience a plastic hinge near the base, and it will undergo large deformation without significant increase in the lateral load. So if we plot this force versus displacement or moment versus curvature for this particular shear wall, it will look a curve something like this. So this is a typical moment curvature relationship for a member. It can be a beam, it can be a column, it can be a shear wall. So this again, this moment curvature curve of this shear wall or column or beam, we idealized by two lines. So those two lines are represented by this thing. So these are the two lines that are representing the idealized behavior in terms of moment rotation or moment curvature for this particular shear wall. In this line, this point is representing the yield capacity that we can derive by knowing the reinforcement and the material properties. Yield capacity can be determined. Similarly, the ultimate capacity can also be determined. And this length is representing actually the plastic curvature associated with this shear wall. If we know the length of plastic hinge, then if we multiply this plastic curvature by length of plastic hinge, we are able to estimate the plastic rotation capacity of this particular shear wall. So this is a prerequisite for conducting non-linear analysis, that we should know how the force versus displacement or moment versus curvature or moment versus rotation curve for a typical member will look like. That I need to know somehow. So the force capacity I can determine, stiffness I can determine from the shape and size of the member. Force carrying capacity I can determine from the reinforcement that is being provided and the cross section size. So by knowing the stiffness using cross section dimension and shape, I can determine this stiffness, and by knowing the reinforcement, I can determine the my and mu. So now only difficulty that remains with me is to somehow to determine this plastic rotation or plastic curvature that is applicable for this particular shear wall. And this we can determine if provided we have enough experimental evidence on what parameters this plastic curvature and plastic rotation depends on. And accordingly, this force displacement moment rotation curve is represented in the idealized form as shown below, where different limit states, for example, immediate occupancy, life safety, and collapse prevention are also shown. So this plastic rotation capacity of different elements, whether it is a beam, column, or maybe a shear wall, we can determine through experiments. And what type of experiment we need to conduct? So we need to test a beam, column, shear wall, or whichever element we want to, for whichever element we want to develop this m theta curve or m phi curve, we need to test them under reverse cyclic loading that is expected during earthquake. So this is a typical test result that is shown here. So the green curves are basically showing the hysteresis response of a beam that is subjected to, of a column that is subjected to uh, reverse cyclic loading. So you can see that uh, if I connect the peak points over each of these cycles, then I will be able to derive this red color curve which is shown by this envelope that is called cyclic envelope. So what is the cyclic envelope? If I connect the peak points of every cycle of displacement that is being given to this element and obtain a smooth curve, that is called cyclic envelope. And over this, I have overlapped another curve that is shown by this blue curve, blue color curve, that is being obtained from American standard. And American standard defines that how we can obtain this backbone curve for a given particular element, whether it is beam, column or shear wall. So depending on the properties of this particular element, we can determine that how its backbone curve will look like. So this backbone curve is actually required, and it is required for purpose of development of nonlinear model. If we don't know this backbone curve, then we cannot develop the detailed nonlinear model of a structure. So this backbone curve actually depends on how the element is detailed, whether my element is detailed by following the principles of ductile detailing using IS 13920, or it is followed, it is detailed by following the principles of only IS 456 without ductile detailing. Depending on that, the shape of this curve will be different. So ductile curve will have larger area under this curve for this moment rotation curve, whereas the non-ductile curve will have lesser area under the curve for this moment rotation curve, provided they have the same yield moment capacity. So this basically actually accounts for the strength degradation that is expected to occur with successive increase in the displacement during earthquakes on that particular element. So you can see that for the larger uh, displacement cycles, or for these cycles, the strength capacity is relatively less, as compared to these cycles the strength capacity is high. So this backbone curve actually accounts for the strength degradation effects that are going to occur in that particular element at large deformation. So if this information is available with me, I can develop the nonlinear model of a structure. So for example, let's say I have a building that comprises of beams, columns and walls. So to develop the detailed nonlinear model, what I need to do, I need to assign the plastic hinges or the nonlinear behavior at the ends of the beams and the columns. Why I am assigning the nonlinear behavior at the ends only? Because if we see the typical bending moment diagram of a typical frame, then under the combined action of gravity plus earthquake loads, we observe that the maximum bending moment is going to occur at the ends. Therefore we need to assign this moment rotation behavior at the ends only, and the remaining part, intermediate part, we are modeling as the elastic element, and similarly then hinges we are assigning at the ends of the beams and columns at all the junctions. So and then we can also model the stiffness, also stiffness of the infills, and their capacity in different failure modes also. So this typical m theta curve or m phi curve is shown here, that we have already discussed. So if we know this m theta behavior uh, and the reinforcement detailing of this particular element cross section size, then we can develop this m theta curve and we can assign these plastic hinges at the ends of this particular structural uh, assembly. Now after assigning these plastic hinges, now my objective is to develop the force displacement relationship of a building, because ultimately we need to estimate the force versus displacement relationship for that particular building. So after assigning those plastic hinges at the ends of these different members, I need to apply gravity as well as lateral load simultaneously, and gravity load will be constant, whereas the lateral loads will be continuously increasing, and those loads will be increasing up to the point where the structure becomes unstable or a predetermined limit state of interest is reached. So if I push the structure by applying the gravity and lateral loads, so initially the structure will show elastic behavior. After certain point it will yield and it will show the inelastic behavior as shown here. So this is a typical force versus displacement curve of a real structure that we discussed earlier. This curve actually helps us in obtaining the global behavior of the structure, as well as what are the weak links that are present in that particular structure. For example, where the hinges or where the yielding will occur in that particular structure, that we will see in the subsequent slide. So let's say I want to conduct the nonlinear static analysis. So the typical flow to conduct the nonlinear static analysis is, first I need to apply gravity load that we apply usually in a static analysis, and then in addition to gravity load we also need to apply the lateral load. The pattern of the lateral load I need to choose appropriately, such that the deflected shape of the structure under the applied lateral load should be as close as possible to the actual deflected shape of the building during earthquake. If I can predict what will be the deflected shape of the particular structure, and I need to choose the lateral loading pattern in such a way so that that lateral loading will also that particular lateral loading will also result the same deflected shape of the structure that I am expecting during earthquake. That type of loading is the ideal for the purpose of pushover analysis. But in reality, we may not know that particular type of loading. So there are certain rules that are established. For example, if your response of structure is dominated by fundamental mode of vibration, then this loading proportional to fundamental mode is well enough, because response is dominated by that mode of vibration. So if you are applying lateral loading pattern in that particular mode only, then your deflections will also be in close resemblance to the actual deflection that are going to occur in the structure. After applying the both gravity as well as lateral load, you will be able to estimate the force displacement relationship and also the structural failure mechanism, where the hinges are forming, where the yielding is occurring, where the members are reaching to immediate occupancy, life safety, or collapse prevention limit state. So let us try to understand the typical how nonlinear static analysis can be conducted. So if we have a structure that is subjected to lateral loading, and we have applied this moment curvature curve for every beam and column, it will be different, and we have assigned the corresponding moment rotation curve to each of these beams and columns which are present in this particular structure. So after applying the gravity loads and lateral loads, let's say I am pushing this by this loading. So after pushing initially this structure will behave in a linear manner. So I will get base shear versus roof displacement response as a straight line, and my member response will be within the elastic limit. Then only this force displacement relationship will be will follow a straight line. Then if I further increase this load, then some of the members will reach to yield point, and accordingly up to yield point the force displacement curve will also be straight line. Now if I further increase the load, then some of the member which have yielded in the previous cycles will lose its stiffness, because now the member is not having stiffness. This curve becomes almost elastoplastic, so there will be reduction in the stiffness because of the some of the members have already yielded. So now structure will follow the force displacement curve on this path. So initial the path was this straight line, because there was no reduction in stiffness. After yielding of some members, there will be reduction in stiffness. If I further increase the load, there will be further reduction in stiffness because of the yielding of more number of members. And if I keep on increasing the lateral loading, so a curve kind of shape with linear elastic region and then a curvilinear portion I will get, and there will be segments which will be piecewise linear, because in every successive increment the structural response which we are estimating based on a linear analysis only. So by this we can obtain this base shear versus roof displacement curve, and that is called pushover curve. So this is the pushover curve, and this is representing the typical mechanism of the yielding. So for example, this member has yielded, this particular member has reached to near to this collapse limit state. Similarly, this member has reached to collapse prevention limit state. This member has reached to life safety limit state. Likewise, so we will have a clear picture that where the yielding is occurring, which members have yielded, which members have not yielded. After knowing this force versus displacement relationship, because we are performing analysis on a multiple degree of freedom system, and the earthquake response or the earthquake demand that is usually available to us are in terms of in the response in terms of response spectrum that is applicable for single degree of freedom system. So to compare the earthquake capacity of the structure with earthquake demand that is available with us in terms of response spectrum, first we need to idealize this multiple degree of freedom system into equivalent single degree of freedom system. So force displacement curve that we have obtained for multiple degree of freedom system can be converted into equivalent single degree of freedom system by using certain transformations. Those are written here. So from this exercise we are converting them on the same scale, because our demand is for multiple degree of freedom system in terms of V versus D, and our our capacity is in terms of V versus D for a multiple degree of freedom system, and our demand is for single degree of freedom system. So to bring them on to the same scale, both should be corresponding to single degree of freedom system, because our demand is also corresponding to single degree of freedom system. So we have converted this from response of a multiple degree of freedom system to the response of a single degree of freedom system. Once we know Then after this, we also need to do bilinearization of the capacity curve. That means because our actual force displacement curve is in the form of a curvilinear shape, and it is easier to deal with lines rather than a curve. So there are different methods by which we can convert them into equivalent bilinear curve. And after knowing the yield point and ultimate point, we are able to estimate the yield acceleration, the yield displacement, and ultimate displacement. And these parameters are called actually the capacity curve parameter. So these are representing structural capacity. Now, after estimating the structural capacity, the next task is to estimate the structural demand. So the structural demand means how much the inelastic displacement the structure will undergo when it is subjected to earthquake. If I can estimate that, I can compare the structural capacity with seismic demand, and then I can decide and I can determine how that particular structure is going to behave during earthquake. So to determine this seismic demand, there are variety of methods that are available in the literature, and this displacement modification method is the simplest method, which modifies the elastic displacement by certain factors to take care the effect of site class as well as inelastic effect associated with the buildings. So here the target displacement or the expected displacement of a structure during earthquake can be computed as C naught C1 C2 times SD elastic, where SD elastic is nothing but SA into T square by 4 pi square. So these quantities are known to me. TE and SA are known to me from the SA I can obtain from response spectra, and TE I can obtain from the equivalent bilinearized pushover curve using certain formulation, and I can determine what will be the value of delta T. So once delta T is known, that means I know that how much displacement is going to occur in that particular structure during earthquake. So displacement that will occur during earthquake is known to me, and structure capacity in terms of force versus displacement is also known to me. So now I can compare them to obtain the seismic performance. So how seismic performance is obtained? So seismic performance is obtained by combining the capacity curve with demand curve. So demand curve is nothing but a response spectrum, and capacity curve is nothing but the force displacement relationship that we have developed corresponding to a equivalent single degree of freedom system. Why we need to take corresponding to equivalent single degree of freedom system? Because response spectrum is always defined for a single degree of freedom system. Therefore, the force displacement curve also we need to convert into equivalent single degree of freedom system. Then only they can be compared. So if I superimpose the structural capacity and seismic demand, then I will get some certain intersection point over this curve. This point is representing basically that this particular building will experience this much of displacement if an earthquake is occurring. And for this particular structure, depending on different displacements, I can also mark what is the threshold displacement where immediate occupancy is expected, what is the threshold displacement where life safety is expected, what is the threshold displacement where collapse prevention is expected. So this I know for my structure, and for this particular earthquake, this structure will undergo this much earthquake. That means displacement is actually exceeding life safety, but it is less than collapse prevention. So from this exercise, I can conclude that my structure will be able to achieve collapse prevention performance level during this particular earthquake. So this completes the discussion. So major conclusion from this particular discussion I can conclude is that strength, stiffness, and ductility play a crucial role in earthquake resistant design of structures. That is what we have understood. The prescriptive force-based seismic design results in unpredictable seismic performance of the structure throughout the design space, as we have discussed equal displacement and equal energy rules, and we have seen that R is equal to mu and R is equal to square root 2 mu minus 1, depending on which type of structure we are talking about, whether it is long period or short period, and their performance can be different, but we are using the same response reduction factor, whether it is short period or long period. And in some cases, intent of collapse that is written in forward, intent of code that is written in forward in terms of no collapse may not be achieved under a major earthquake, because we are nowhere ensuring whether the structure will be able to meet this requirement or not. We are just doing what is given in the code. So nonlinear static analysis helps us in realistically typically estimating the seismic capacity of the structure, and it overcomes the issues that are related to force-based seismic design. And nonlinear static analysis helps us in understanding the progression of yielding or failure mechanism of weak links of the building. So depending on whether hinges are forming, we can identify what are the weak links, what are the strong links associated with the building. And if we want to change the structural failure mode, that can also be done by modifying the structural design. And nonlinear static analysis also provides an alternative method for seismic design of code exceeding buildings. So for buildings where the code provisions are not applicable, in that case, we can conduct actual nonlinear analysis and we can see what will be the realistic values of different parameters that can be used for their structural design, that can be verified through this nonlinear static analysis. So with this, I conclude my presentation. Thank you very much for your attention. And please let me know if you have any questions. Thank you.
Thank you so much, sir. Thank you, Dr. Surana, for covering the different aspects of seismic analysis, the modeling strategies, the difference between the performance-based seismic design and the prescriptive design, along with the complete detailed process of nonlinear static procedure and its importance. Nisha, over to you. Nisha?
Thank you so much, sir. Thank you so much, sir, for giving your valuable insights on such an important topic of, about how seismic analysis is conducted and how equivalent static force is completed regarding the behavior of buildings under earthquake, and how strength, stiffness, and ductility plays a very crucial role in earthquake resistant design of structures. So, sir, it's really a great learning experience for all of us, and I can see that there are a lot of questions from the participants who are eager to discuss with you. So now I request Dr. Praveen, sir, to please read out the questions to Dr. Surana.
Sure. Sir, can I take the questions? Dr. Surana? Sir, is my voice audible to you? I think just a minute. I request all the participants to stay tuned. There is a technical glitch from Dr. Surana's side. He will be joining shortly. And then we will take up the questions which have been asked by the different participants. Kindly stay tuned. Dr. Mitesh Surana will be joining shortly. Kindly stay tuned, please.
Hello, Praveen, can you hear me?
Yes, 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 yes.
Yeah. So I have joined with some other computer because in that computer
Okay,
some
okay,
issue is there.
okay.
Yeah.
No issue, no issue. I'll read out the questions for you.
Fine, no issue.
Mhm. Uh, the first question is how to program nonlinear static pushover in MATLAB. Is there any code available?
No, that code is not available. At least it is not available with me. But of course,
Okay.
there are several codes at several platforms that you can see that can help you,
Okay.
because it depends on uh, what type of modeling method you are using. Because I have just discussed one type of modeling method, for example, lumped plasticity, right?
Right.
There are several
Right.
other types of modeling techniques that are being used to
Approaches.
model nonlinear behavior of a structure.
Hmm.
So they need to look for that aspect also. Particularly subroutines you can find out in the OpenSys community. There are several programs
Okay.
related to different types of analysis or different purposes. Yeah.
Okay. Okay. Thank you. Uh, this question is related to infill wall. Is there any specific hysteretic model which you recommend to simulate the behavior of an infill wall?
No, it is. I cannot recommend any specific model. There are several
Okay.
models that are available already in the literature, right?
Hmm.
On infills, there are extensive experimental investigations that have already
Data
been
is there.
conducted. So that can be looked upon. So one of the model that is being used mostly in the recent literature is a trilinear backbone curve that is being developed by Burton et al. So there
Burton.
is a paper
Right.
by Burton in AC, Journal of Structural Engineering.
Right.
I don't remember the year, but it is maybe 5 to 10 years old or so. So that
Okay.
is
Okay.
also used in, and they have their, I think, own code for that also.
Okay.
SPA infill, static pushover
Hmm.
analysis of infill. They have their codes on their website, so they can go through them.
Okay. The next question is, what is the displacement limits for general buildings?
Displacement in buildings, actually we are not directly defining the displacement limit. Instead, we are defining the interstory drift. That is the considered to be as a performance indicator, because it is not the absolute displacement, it is the relative displacement between two floors that is going to induce the damage in the structure. So typically there are thresholds that are defined in different codes, and typical values ranges for different limit states. For example, let's say if I talk about immediate occupancy, it is typically 1% interstory drift. For life safety, it is 2%, and for collapse prevention, it is 4%. But these limit states are, these are very generic, and these are defined based on extensive testing on columns only, right? So they can differ for building to building, but those type of estimates are not available in the literature at the moment.
When someone is performing the nonlinear static pushover analysis, which type of load pattern one should use?
Yeah, so that is what I discussed during the lecture also. To decide the load pattern, you should understand the behavior of a structure in advance, how the structure is going to behave. So if you can predict what will be the deflected shape of a structure during earthquake, and if somehow you can decide a loading pattern that will produce the same deflected shape, that is the ideal one.
Okay. And what is the basis for choosing a specific type of a load pattern? I think you have already answered this, because there are several types.
Yeah, so specific type of loading pattern, I mean, there is no basis, is only this. Our aim is to be to predict the behavior of a structure as realistically as possible. And it can be only predicted if I know how my structure is going to behave during earthquake. First, I need to know that. Then only I can decide what will be the appropriate loading pattern and what should be the basis. So there can be different loading patterns. There can be comparison between different loading patterns, and there can be wide variations in the results if you are using different loading patterns. That is also possible.
Okay. There is a question related to one of the clause in IS 1893 Part 1 2016. For equivalent static analysis, there is one response spectra available. For response spectrum, also there is another spectra available. What is the difference between these two?
Okay, so as we discussed in the beginning of this lecture only, you must be aware that in equivalent static analysis, we are actually ensuring, we are applying the equivalent static analysis by assuming that the structural response is governed by a fundamental mode of vibration, right? So equivalent static analysis is based on only single mode of vibration. We are not considering the multiple modes in equivalent static analysis. So if you see the shape of the response spectrum that is being given in the code, from 0 to 0.1 second, it is rising for when we are applying the response spectrum method. But it is constant if you see when we are applying the equivalent static. Because we need to ensure that forces are not underestimated when we are assuming that the structural response is governed by single mode of vibration. There can be structure in 0 to 0.1 second period range. For example, single story masonry building that can have a period close to 0.1 second, or even less than 0.1 second also if structure is very rigid. So in those cases, if I am applying the equivalent static method using the response spectrum that is being given for response spectrum analysis, my forces will be significantly non-conservative. So that linear rising branch is only applicable when we are applying response spectrum analysis, and when we are applying the response spectrum analysis indirectly in that particular linear rising branch, the higher modes will come into picture, not the first mode. First mode will be in the constant plateau or decaying part of the response spectrum.
Okay. So the next question says, if a building has a drift ratio of 0.012 at immediate occupancy level, do you think the structure has a good deformation capacity?
At immediate occupancy, typically we expect interstory drift ratio of 1%, right? So what you have said is 1.2.
1.2.
So it is very close to that only.
And the code also has a drift limit, right? It should not be more than 4% of the story height.
No, in Indian code, it is defined as 0.4% at the design earthquake load.
dB, yes.
At the design earthquake load, it should not be less than, it should not be more than 0.4% of the story height, inter-story height.
Okay.
0.004.
0.00. Okay. If the performance point of any structure is coming below the immediate occupancy level, what will be the interpretation in terms of structure's behavior?
So that means that structure is close to elastic behavior. That structure will experience close to elastic behavior.
Okay. What should be the hinge length based on the cross section of an element?
So there are empirical equations that have been developed from the experimental evidence that by observing the plastic hinging region. So there are several expressions of LP that you can find in literature.
Plastic hinging.
Those are primarily dependent on Fy, then the diameter of the bar and the length of the element and so on. These parameters primarily.
Okay. There is a question related to reinforced concrete. Let's say if a concrete has got some tension reinforcement, for example, steel fibers. In such cases, how one can develop the moment rotation curves for different structural elements?
No, I could not get the question. That means
But
somebody wants to develop moment curvature curve for reinforced concrete.
For a reinforced concrete, but here there is no rebar, right? Rather, there is a steel fibers, right?
Okay.
So in that case, is it possible to model in a section designer, or any specific other approach needs to be adopted?
I don't think so that it is possible in section designer. There has to be some other methods that has to be used. No, the conventional method is not going to work.
Okay. There is a question related to IS 1893 again, and it is related to dwell system. There is a clause which states that the moment resisting frame, here dwell system means I'm talking about the moment resisting frame along with the shear walls. The code in one of its clauses says that the moment resisting frames are designed to resist independently at least 25% of design base shear. What is the physical interpretation of that?
That that this clause exists in IS 1893, but still I don't know what could be the reason of this particular clause that frame should be independently designed to resist 25.
Because it says that the load has to be distributed based on the proportion of stiffness.
Yeah,
but minimum to minimum.
Yeah,
moment
what I could sense that if let's say your wall fails, then there has to be second line of defense to resist the loads that are coming on the structure. So that is the perhaps maybe a reason why code says that at least 25% of the base shear you should design for the frame. Frame should be designed for that.
Okay. The next question is how I have to give the input for plastic hinges with the moment curvature in beams and columns.
Input of plastic hinge in
because
if
you talked about the M5 analysis, right?
Yes.
So at the time of assigning the plastic hinges, how to give this moment curvature relationships for beams and columns?
So plastic, basically this plastic curvature ultimately you can convert into plastic rotation by using length of plastic hinge. And then moment versus theta you can directly define for that particular element. So curvature should be converted into rotation, and then m theta can be directly assigned to the member.
Okay. This question you have already answered, but the participant is asking that for short period structures, less than 1 second, having SMRF frame, you said you need to take R equals to 3 and not 5. That he is corresponding to R is equals to square root of 2 mu minus 1.
I am not saying that R equal to 3 should be taken. I am saying that according to equal energy rule, R will come out to be, if that particular system has a ductility equal to 5, then for that structure, R will come out to be 5. But instead, we are still taking R will come out to be 3 when mu is taken as 5. but still we are taking R as equal to 5. This is a problem of force-based design. We are not taking care of this effect even though we are knowing it.
Right. Okay. Sir, in the performance curve, can we study the behavior of the structure beyond the collapse prevention?
Beyond the
Collapse prevention.
collapse prevention. Yeah, you can study, but the problem is that most of the software or commercial package or any program you use, you will not be solve the problem beyond the collapse prevention, because there will be sudden drop in the strength and
Decrease
that
in the
type
load
of
capacity.
decrease in the load capacity, and that type of behavior you cannot solve using any type of algorithm that are available till now. So
Okay.
you will get instability in convergence and those kind of issues. Numerical instability will arise. So it is difficult to solve.
Okay. There is a question. During pushover analysis, what is the targeted displacement should be considered during analysis? Is it 0.04 times of H?
0.04 times of H. Yeah, that means you are targeting up to 4% of the total height of the building.
4% story height.
So typically 4% we take as a threshold for collapse prevention, right? We have discussed interstory drift, right? So if you are taking even less than 0.04 H, that is also fine, because what happens when a structure will deform, not all the stories will undergo the maximum interstory drift. Maximum interstory drift will be there only in few or any one of the story. Other stories will have a drift less than that. So 4% maximum interstory drift will be achieved when the total drift is less than 4%.
Okay. And the next question says, what is the fundamental difference between the force-based and displacement-based analysis, especially in the context of performance?
In context of performance. So we have already discussed that in displacement based analysis, we are already checking whether what we are intending, what we are targeting is achieving or not.
Right.
We do not do this in case of force based analysis. We just do what is given in the code and that's it. What will happen to the structure, that we will leave. We nowhere check.
Okay. Is there any restriction for the default value selection for concentrated plasticity from ASC 41?
For lumped plasticity, default values.
Yes.
Can you repeat the question?
Is there any restriction for the default value selection? Is there any limit for concentrated plasticity if I model from ASC 41?
So there are no limits, provided we need to understand few differences. For example, ASC works on cylinder strength, right? In India, we work on cube strength.
Right.
So these type of things we need to incorporate while choosing the appropriate value from the ASC. Otherwise, what we are taking and what actually ASC mean that we should take will be different. So likewise, first we need to understand that what are the differences in terms of ASC and Indian standards. Those should be understood. Then only you can take some values from those standards by establishing an equivalence.
Okay. Can performance levels like immediate occupancy, somebody has shared. Okay. So the question is, can performance levels like IO, damage control, life safety, can be estimated from maximum total drift and maximum inelastic drift?
Maximum total drift.
Can we estimate the performance levels?
Just directly from the drift, I think it will not be possible to estimate the performance levels. It is difficult to estimate performance level just from the total drift. Total drift,
But
you mean by roof drift, right?
Roof drift, yes.
Right. So it is difficult to estimate directly from the roof drift.
Okay. Okay. So the percentage you said that for immediate occupancy it is 1.2%. For collapse prevention it is 4%, right? So these values are coming from
Are
some specific
interstory drift.
research.
These are
Interstory.
interstory drift,
Okay.
and these are coming from the experiments that have been conducted on several components. For example, these limits 1%,
Right.
2%, and 4% are applicable for ductile detailed buildings. That means SMRF building. These are not applicable for
Right.
non-ductile buildings in which ductile detailing has not been followed. So large number
Okay.
of columns and beams and their assemblies have been tested in the past. A data was collected, and then these values were arrived that 1%,
Okay.
2%, or 4%, depending on the observation in terms visual observation in terms of at 1% drift, how much, what type of cracks are developed, at 2%, 4%, what was the state of the element that was experimented, and
Okay.
then those thresholds were reached.
Okay, sir. So we are left with only two questions. The question says, what is the fiber hinge modeling approach for pushover analysis?
Hmm. So in fiber hinge modeling, you need, instead of defining the likewise in the lumped plasticity, we have defined a plastic hinge uh, concentrated at a point, uh, and to that hinge we have assigned moment versus rotation, right?
Hmm.
In fiber hinge modeling, you need to define the you need to discretize your section into small fibers. Those fibers will be corresponding to confined concrete, unconfined concrete, and steel, which is being provided in the section. Each of them will have different properties. Confined concrete will have different stress strain behavior. Unconfined concrete will have different stress strain behavior, and steel will also have different stress strain behavior. And accordingly, then you need to use it. So it is completely different than lumped plasticity approach, where you are directly assigning force versus displacement relationship of the element. Here you are assigning the material
Hmm.
level behavior. It can be
Right.
stress.
Uh, there is a question which says that sometimes it has been observed that the base shear versus displacement curve does not reaches up to the defined target displacement. What could be
Hmm.
the possible explanation for that?
So yeah, there can be two reasons. One is that your structure has become unstable before that. That means structure has become
Hmm.
mechanism. So it cannot take any more force. This is one reason. Second reason is some software shows instability, particularly when hinges are formed in the column first as compared to beam. This is something related to convergence plus the algorithm that is being implemented in the softwares. So in that case also, sometimes you will find that few hinges are formed in the column and your analysis will stop and you will not be able to perform the analysis. Even the structure has capacity to resist
Hmm.
the load.
Hmm.
So these are the primary reasons that I also encountered during I was studying, and also now also I encountered when I discuss with my students.
Right. Right. Uh, Sir, most of the questions I have read, whatever is clear to me. Now I uh, request all the participants, if there is any specific question which you want to ask directly to Dr. Surana, you're most welcome. We have another 5 minutes. We can utilize this time for another discussion. Anyone from the audience who want to directly raise the question, they can unmute and they can ask the question to the speaker directly.
Hello.
Yes.
Hello.
Yeah, is it
No,
Mr.
sir.
Shashi?
Yes, sir. Yes, sir. Actually, my
Shashi,
question is
please
related.
ask your question.
Sir, actually, my question is related to same because I am a PhD scholar, research scholar. In concrete, I am using
Okay.
the steel fiber and I am making the moment curvature in section designer.
Okay.
So after making the moment
Hmm.
curvature in SAP 2000, I have to re-input
Hmm.
that data into the plastic hinge. So that is two
Okay.
problem is coming. The moment curvature when I am giving the steel fiber, steel fiber at the initial stage in the material level, and after confinement, when are re-inputting the things to getting the moment curvature, I had also uploaded one of the photo there, sir. So the question is that how we will go for the plastic hinge parameter, because there we will select the ASC 4117. So by default value it is written in SAP 2000. But if we have to input the value, how we have to input the value for the plastic hinge? That is the question again, sir. It is not clear to me. Can you elaborate this thing, sir?
Okay.
So you mean that you
Dr.
want to define user-defined hinge, right?
Yes,
Dr.
sir. Yes, sir.
Surana, there is a photograph in the chat box. If you can, if you could see the moment curvature curve, there is a snapshot given.
I could not see any moment
Slightly
curvature.
up, slightly up.
No, I could not see that where that moment curvature curve is.
Shashi, it would be great if you can
Sir,
share your screen and
I
show that
uploaded.
photograph.
Sir, I uploaded again
Uploaded
the
now.
photograph, sir, in chat box.
Okay, okay. Just a second. It is still, yeah. Dr. Surana, can you see
Yeah,
now?
now it is coming.
Yes.
Yes. So what
He
is your
want to
question
give
now?
this input. He need to give this input for plastic hinge with this moment curvature in his beams and columns. How
No, he will
he
not be able
gonna
to give
define?
this as an input, I think.
Yes.
In SAP, because there is a predefined table where you can give a limited number of points. It could be 4, 5, or
Pattern,
something like
yes.
that. So that pattern you have to follow. You have to convert this curve into equivalent curve that will be representing that shape, which is predefined in the
Yeah,
SAP or
yes सर, आई
Yes,
गॉट द
Shashi.
पॉइंट। सर मेरा ये है सर कि जैसे इसको इक्विवेलेंट डायग्राम बना लेंगे, इसको इक्विवेलेंट डायग्राम मैंने
ठीक
इक्वल
है।
एरिया से बना लिया। उसके बाद मैं वहां पे जाता हूँ प्लास्टिक हिंज में, और जब इनपुट करूंगा तो बीम वाले पार्ट में तो उसने दे रखा है कि आप मोमेंट और कर्वेचर दोनों इनपुट कर सकते हैं, लेकिन कॉलम वाले पार्ट में वो कहता है कि वो जो एमवाई की वैल्यू है वो बाय डिफॉल्ट पिक करेगा, वहां पर वो रिस्ट्रिक्शन नहीं देता है, तो वो एमवाई की वैल्यू इस
I
वाले
think
कर्व से।
the problem is if you are able to define it for beams, but if you are not able to define it for columns, then there is certainly problem with axial force. In column, axial force is also coming into picture. So are you taking into
Right.
consideration that axial force? Because in columns, you need to define moment curvature curve for multiple axial force values. Then only
Yes, sir. Sir,
different you
sir,
can
in
do.
SAP 2, sir, excuse me, sir. In
Huh.
SAP 2000, two things
बोलिए।
is there. PM to M3, PM to M3, I am inputting, and also the moment curvature parameter is asking. So for column, sir, he is saying like that, it will take the MY value by default from this parameter, from moment curvature. So if I am giving the by default value, what the MY is coming, so which value it will take from this
I
curve?
think,
My
Shashi,
question is that, sir.
it is better that because I need to understand first problem. Still, I am not getting too much clarity. So first, I need to visualize that what is the problem actually. So it is better that you can send your problem to my email ID. Then we can discuss
Okay,
it.
sir.
This because first I need to understand where is the problem. Then only I can answer. Otherwise,
Okay.
Okay, sir. Okay, sir.
yeah.
Okay,
Can I
Shashi,
share
you
my
can
screen,
write.
sir? Sir, actually, if you have a time, can I share my screen and can I open the SAP or everything?
Shashi, we are already getting delayed. As sir said, you please mention your problem in much detail along with snapshots and everything. Write to him, okay, on his official email ID, and he will revert to you. Okay.
Sir, from where I will get the official email ID, sir? Please, sir.
Through sir's official website. You go to IIT Ropar website, Department of Civil, you can find Dr. Mitesh Surana.
Okay, sir. Okay, sir. Thank you, sir. Thank you very much,
Okay,
sir.
Sashi. Okay, thanks. And the last question is, sir, what is the load transfer mechanism in the shear wall components?
Shear wall components means shear wall.
How the load transfer mechanism? Yes, what is the load path in the shear walls? How the load is getting transferred, especially the lateral loads?
So primarily shear wall is deforming in the bending mode, right? So how the load is being transferred in the beams? In the similar way, the load is being transferred in the shear
Similar.
walls.
Okay.
Shear wall is nothing but a vertical cantilever. So you can assume a vertical column. How the load is being transferred in vertical column? Same in the same way the load is being transferred in the shear wall. So shear wall is nothing but a wide column. That's it.
Doctor, right. Dr. Narayan, do you have any specific question? There is one
Yes, sir.
point you raised in the chat box. It was not clear. It was related to performance-based design related to displacement. Could you please clarify your question?
No, so I have little different question. Can I ask that, sir?
Yeah, please. Go
Yes.
ahead.
So in ASC, they generally use the cyclic loading protocol, like non-linear, quasi-static cyclic loading protocol. How they are using it in design? Actually, in whatever discussion I am hearing in India, we don't discuss that. Miss, I have not even heard that even once, that how we are using the quasi-static cyclic loading, that loading displacement loading protocol in design. So whenever I
Actually,
see ASC,
yeah,
yes,
Dr.
sir.
Narayan, just let me answer. That quasi-static loading pattern that you are discussing, actually that is to conduct experiment as far as what I understand. It is not being used in design. The backbone curves which I have discussed, you must know that I have discussed hysteresis curve, right? You remember?
Yes, yes, sir, yes,
So
sir.
That is the green
how
color hysteretic
how the
loops.
loading
Yes.
should be applied to obtain those hysteresis curve, that is what is defined as the loading protocol. Because if you are, let's say, how many number of cycles you should use for the same type of displacement, up to what displacement you will go, what will be the increment in displacement in successive cycles, those things are defined in those loading protocol, and that are to be used to develop the component hysteresis curve and backbone curve. So I think that is related to this, what you are discussing. It is not related to design. It is related to how we are obtaining the hysteresis curve and backbone curve, which are used in nonlinear static and nonlinear dynamic analysis.
So we will actually we will need it for the preparation of the backbone curve. So
Yeah, if you want to conduct the this nonlinear static analysis, nonlinear dynamic analysis, actually we need to develop such type of backbone curves for Indian code detailed beams, columns, shear walls, and so on. Such type of experiments are very few till now, and many people are, or some people have done experiments, but they have used different loading patterns. So there is no uniformity. So loading pattern should also be have some time, some standard. Then only you can make common consensus, right? Or you can generalize the result. If you are testing in some other loading pattern, I am testing in some other loading pattern, somebody else is testing in some other loading pattern, right? Then the result will become loading pattern dependent.
so
So
sir,
to
the
Then we
avoid,
cannot
backbone.
generalize that.
a general recommendation is given in the ASC.
Yes, sir. So, sir, that design part means you use that backbone curve in the design part. That
Yeah.
backbone curve. That
So those backbone curves currently we have not Indian code do not specify any kind of backbone curve, right?
yes,
So
sir.
we need to rely on
Yes.
other codes.
Yes, sir.
And what is the rational or what is the logic to rely on other codes? Because if we have the detailing provisions that are comparable to what is given in the ASC, then whatever the test result they are getting, we are also expected to get the similar kind of results, right? Provided the detailing which they are recommending, we are also having at par the same type of detailing, because backbone curves are mainly dependent on detailing of the element.
Yes, sir. Yes. Thank you, sir.
Okay, I hope Dr. Narayanan's clarification has been cleared. Sir, the last point, uh, what is that document which you are referring where this drift limit of 1, 2, and 4% corresponding to IO, LS, and CP is recommended? Is there
I
any
think
specific document?
1, 2, and 4% is recommended in some of the document of FEMA. Exact number I don't know, but it is related to
Okay,
maybe FEMA
okay,
356 or 273.
okay,
I don't remember, or 440. These three are the
okay, okay,
primary document. In one of them, it could be found out.
okay, okay. Okay, sir, thank you so much. Thank you so much for clearing all the doubts of our participants. It's over to Sujit. Sujit, are you there? Yes.
Yes, sir. Good evening, everyone. I am Sujit Kumar, PG first year student pursuing MTech in Computer Aided Structural Engineering at IIT Hyderabad. It's my privilege to propose the vote of thanks on behalf of IS Trustee, IIT Hyderabad, a student chapter, for this occasion. First and foremost, I would like to thank our guest speaker, Dr. Mitesh Surana, for sparing his time to grace today's webinar. Sir, I thank you for sharing your valuable knowledge on the topic earthquake performance assessment of buildings, non-linear static analysis, which is of great interest to all structural engineering community. Sir, the insights we received today about non-linear analysis of a structure were extremely informative in addition to the existing knowledge we have gained about linear analysis. Concepts such as force displacement relationships, capacity spectrum, seismic demand, which constitute an important aspect of non-linear analysis, were explained in a very interactive manner, making it more and more easier to understand. I would like to express our heartful gratitude to our mentor, Dr. Praveen, for his valuable guidance and timely suggestions. My sincere thanks to Mr. Srikant and Mr. Mahesh from IT team and Ms. Babita and Ms. Grace from design team for providing all the logistic support, help and assistance. I thank the program coordinator, Dr. Sunita Paliseri, for her continuous encouragement. I also thank to all those who have directly or indirectly helped us to make the event more successful. My special thank to all the participants for their enormous cooperation. Last but not the least, I also want to acknowledge the effort, support, and cooperation of my entire team in making this event successful. Finally, I want to end this program by extending my sincere gratitude to all of you for being with us and making this event more successful. It was indeed a great pleasure. This concludes our event. Thank you all for attending. We hope you have learned and enjoyed this session. Thank you.
Thank you. Thank you, Sujit. Thank you, Dr. Sirana. Thank you for accepting our invitation, and thank you
Thank you very
for
much.
all the insights related to nonlinear static analysis.
Yeah. Thank you.
Thank you so
Okay.
much.
Okay.
Okay.